The RC circuit discussed in the previous slide is interfaced with the dual comparator module with SR latch found on newer PIC microcontrollers. The voltage across the sensor capacitor, labeled VCS, is used as the inverting input to both comparators. Comparator 1 uses the internal reference voltage available on newer PIC microcontrollers, set to approximately 2/3 of the supply voltage. Comparator 2 will need an external reference. Therefore, we use a simple voltage divider to produce a voltage of 1/4 the supply voltage on the comparator's non-inverting input. The 0.1 microfarad capacitor is added to reject high-frequency noise from the power supply and ensure a stable lower limit voltage. We are using the comparator to create a window of operation. If the voltage across CS drops below 1/4 VDD, the output of comparator 2 will go high. Looking closely at comparator 1, notice that the output's polarity is inverted. Therefore, if the voltage across CS rises above 2/3 VDD, the comparator 1 output will go low. Both comparator 1 and comparator 2 outputs enter into the SR flip-flop's set and reset inputs respectively. Let's explain how this will work. In this slide, note the SR latch's truth table. If the set input is driven high, the pin connected to the Q bar output of the latch will be driven low. If the reset input is driven high, the pin connected to the Q bar output will be driven high. Looking at the condition where both S and R inputs are high, we notice that the operation of the latch will be in reset mode, since this latch is reset dominant. More importantly is a condition where both inputs are driven low. What happens in this condition is that the outputs of the latch will hold the last known output values. As you will see, this will become important in the operation of our relaxation oscillator design. Let's step through the operation of this oscillator. The graph on the right represents the voltage across the sensor capacitor. We will indicate changes in the SR latch state by highlighting the appropriate row in the SR latch truth table in green. Starting at the very beginning of operation, device power up, the voltage across the sensor capacitor is 0. Therefore, comparator 2 output goes high, while the inverted output of comparator 1 goes low, since both inverting inputs are less than the non-inverting input threshold voltages. This places the SR latch into reset, driving the Q bar output to 1, which in turn charges the sensor capacitor. As the voltage across the sensor cap increases, it eventually surpasses the 1/4 VDD threshold, the non-inverting input voltage to comparator 2. This causes the output of comparator 2 to go to 0. Referring to the SR latch truth table, this condition holds the last known output value on the Q bar output at 1, and the sense capacitor continues to charge. Once the voltage across the sensor capacitor exceeds the internal voltage reference on the non-inverting input of comparator 1, the inverted comparator output connected to the set input goes to 1, driving the Q bar output of the SR latch to 0. The sensor capacitor then starts to discharge. Once below the 2/3 VDD threshold, the output of comparator 1 goes to 0. This places the SR latch into the hold state, allowing the sensor capacitor to continue discharging. The voltage across the sensor capacitor eventually drops below the 1/4 VDD threshold, causing the comparator 2 output to go to 1, driving the SR latch Q bar output high. This once again begins charging the sensor cap. This charging and discharging process repeats as long as there is power to the system. We have implemented the RC circuit containing the sensor capacitor into a very good relaxation oscillator. As the capacitance changes in the circuit, so will the RC time constant, changing the frequency of oscillation. So let's look at how we will determine a sensor touch based off of this frequency change using a frequency measurement circuit. We should first note that the output from the SR latch on pin C2 out is actually a square wave. Connecting the SR latch output on C2 out to the timer 1 input pin T1 CKI, we could use this square wave as the timer 1 clock source. Configuring timer 1 register to increment on every positive edge of the square wave allows us to count the number of clock pulses. However, this isn't enough to determine the frequency of the square wave. To do this, we will need to have a fixed period clock source to gate the 16-bit timer 1 value to. For this, we use the timer 0 module. Here, the PIC MCU is configured to generate an interrupt when the timer 0 register overflows. Therefore, the interrupts will occur at a fixed rate. We could detect a change in square wave frequency by observing a change in the timer 1 register's values on each timer 0 interrupt. Capacitance created by the pad alone results in a corresponding square wave frequency. On a timer 0 interrupt, we read the current count value in the timer 1 registers and store it for later reference. Once a finger touch is introduced, the sensor capacitance increases. This increases the RC time constant, effectively decreasing the frequency of our square wave output. Therefore, on the next timer 0 interrupt, when we read the contents of the timer 1 registers, we should get a smaller value than the previous interrupt. Using a software algorithm to compare both values, we can identify a sensor touch. In the above diagram, the frequency difference is exaggerated in the interest of highlighting these changes. In reality, we can expect a frequency change of between 1 and 5%. Once the finger is removed, sensor capacitance is again reduced. This decreases the RC time constant and increases the frequency of the square wave. The next timer 0 interrupt reads the value of the timer 1 registers, recognizes that it is greater than the previous result, confirming that the sensor is released. The hardware section of our system is essentially completed. We will now move on to the software component. To accurately detect a change in frequency of the relaxation oscillator, 2 variables and 1 constant are used. The average variable keeps a running average of 16 previous samples from the timer 1 registers. This running average is used to eliminate noise created by changes in temperature, voltage, and environment. The raw variable holds the current value in timer 1 registers, and the predetermined trip constant is the minimum difference between the raw data and the average value below which indicates that the sensor has been touched. Implementing this in a software routine, on a timer 0 interrupt, the current data is read into the raw variable. If the average value less the trip value is greater than the raw value, a sensor touch has occurred and the software responds accordingly. Otherwise, the sensor is determined to be untouched. If a sensor touch has not occurred, the current value in timer 1 registers is averaged into the 16-point running average. The timer 1 registers are always cleared at the end of every timer 0 interrupt routine, and the CPU returns to whatever it was doing prior to the interrupt. This completes the basic system. These are the fundamentals of a basic capacitive touch system. Let's take a look at some resources available from Microchip that will help you move beyond the basics.